Hello everyone, this is Jennifer Bassett from Level Academy Boosters. Today I came with another video. This is chapter 29 and it is a log-based concurrent data structures. And this is the follow-up from chapter 28. If you remember chapter 28, we discussed about different log structures like footex, wake up in the waiting race, sleeping instead of spinning, just yield, ticket log, fit and out, and load link and stop condition. And we have seen also Linux and concurrent swap and the others. Okay, so this was some of the implementation of logs to avoid critical section problems. And that is a continuation. Today we are going to see chapter 29. So let's get into it. So log-based concurrent data structure. I advise you to read the book as well and to give you some points. Adding logs to a data structure makes the structure thread-safe. This is obvious. And how logs are added determine both the correctness and performance of the data structure. We have a lot of data structure, so how we can add the log system to validate the shared memory issues. That is the idea. So the first one is the concurrent counter without log. This is one of the solution, but the problem is this counter without log is simple but not scalable. That is the problem. As you can see here, we have the counter t into value. So this is the counter t. If you see in the int counter t, we have the pointer and the pointer value. The value we set it to 0. Then for the increment, for the decrement, and for the get functions, as you can see here, for the increments, we have the value we increase, and for the decrement we decrease. Then return the value. This is simple, but the problem with this code is it's not scalable because it is without log. So the concurrent counters with logs, these are a single log. As you can see here, we have a log here. The log is acquired when calling a routine that manipulates the data structure. So what is the difference? If you see here, we have the main, here the counter t function, then int value, then the pthread log t. So we have one log here. So the counter t is here. Then for the set int, for the increment and decrement, here the counter value is set to 0, but as you can see here, we have the log function. The mutex initialized, the log function is initialized, and in the increment also, as you see, pthread mutex log, and we have also, so it is sandwiched between the log and the unlog. So the decrement and the get function also the same, it is sandwiched. You see, get the value, C is going to value, then we have the log function here and the unlog line here, and the get also the same. So the performance cost of the simple approach, if you see here, each thread updates a single shared counter, and each thread updates the counter 1 million times. So this experiment was done in the iMac with 4 Intel 2.7 GHz 15 CPUs As you can see here, the performance of the traditional vertical sloping approximate counter is the threshold of sloping S is set to 1024. And as you can see here, we have trade in the x-axis if you have time second in the y-axis. And if you see the precise once the trades are increasing, the time also increase together. But the slope in the approximate method 1, 2, 3, 4 they are performing well. So synchronized counter scales fluidly. This is the conclusion from this experiment. So perfect scaling, we want to get a perfect scaling, that is the idea. Even though more work is done, it is done in parallel. And taken to complete the task is not increased. The approximate counter works by representing single local counter via numerous local physical counters on per CPU cores and a single global counter, and there are also locks. So how the locks is one for each local counter and one for the global counter. Example, on a machine with 4 CPUs, we have 4 local counters and 1 global counters. This is also very important points it should be in mind. And the basic idea of approximate counter, when a thread running on a core wishes to increment the counter, so it increments its local counter, and each CPU has its own local counter. So threads across CPUs can update local counters without continuation, and the counter updates are scalable. The local variables are periodically transferred to the global counters. Acquire the global log, increments it by the local counter's value, and the local counter is then reset to 0. These are some of the points you should bear in mind. And the basic idea of approximate counter, how often the local to global transfer occurs is determined by the threshold S. This is slopiness, we call it slopiness. So the smaller the slopiness, the more the counter behaves like the non-scalable counter, and the bigger the slopiness is, the more scalable the counter. The further off the global value might be from the actual counter. So if you want to make it more scalable, we have to increase the slopiness value. Let's see this example, approximate counter example, which is given in the book. Tracing the slopy counter or approximate counter, the threshold S is set to 5. Okay, the threshold set to 5. There are threads on each of the 4 CPUs. Let's assume we have 4 CPUs. CPU 1, 2, 3, 4. This is the CPU. Okay. So each thread updates their local counters L1 up to L4. So these counters are in the CPUs. L1 in the CPU1, L2 in the CPU2, L3 in the CPU3, and L4 in the CPU4. And we have the global here. So what we can see here, until the threshold S set to 5, as you can see the first 0, nothing has changed. Then in the time T, L3 and L4 was 1, and global is 0. And in the time 2, L1 is 1, L3 is 2, L4 is 1, and 0. T3, L1 is 2, L3 is 3, L4 is 1. And 4, L1 is 3, L2 is 0, L3 is 3, L4 is 2. And L5, we have L1, 4. Okay. So the local counter was 4, and L2 is 1, and L4 is 3. So when after 5 threshold is 5. After 5 as you can see 5. So the global counter will become 5 from L1 to L1. Again, in the time 7, the global counter become 10 repeats from 4, L4. So this is some of the one of the examples from the book. More explanation is there. So importance of the threshold value is each 4 threads increments a counter 1 million times on 4 CPUs. So Low's performance is poor. The global counter is always quite accurate, and when it is high, performance is excellent, and the global counter count. So what you see in this drawing, this is the sloppiness and this is the time. As you can see, when the sloppiness goes, increases, the time also increases together. So the performance is also scaling. The sloppy counter is like this. So approximate counter implementation, this is also from the code. As you can see, we have the counter T and the int local. This is the global counter, and the global log. We have the mutex T global log, and int local. Again, we have local counter per CPU, and as you can see, number in the CPUs. And pthread mutex T local. We have also another log, and int threshold. This is update frequency. Then in the counter T, here int record threshold, int logs, again int values of all local counts and global counts. So as you can see here, int counter T, and we have int threshold, and C, we have the threshold, C global set to 0. And the P threshold mutex initialize, as you can see, C is G log, and here we have the local set to 0 and pthread mutex initial log. I think it will continue, yeah. Then here in the update, usually just grab local logs and update local amounts. Once local count has risen by threshold, grab global logs and transfer local values to it. So as you have seen here, we have the pthread mutex, and we have log, and assumes greater than 0, this is the local threshold ID, and t greater than 0, and transfer to this one will transfer to the global. And if you come to here, get just return global amount, which may not be perfect, but we have the get counter T, and we have the pointer here, mutex log C, and we have G log, and we have also the global, and we have log, and in the middle it's sandwich as usual, and only approximates. So I encourage you to go to the book again and try to see what each line of code is doing, and basic node structures as well, and basic list structure as well. One used per list. This is the concurrent linked list. This is for the linked list. As you can see, we have head pointer. Okay, so we have the key, and we have the structure node T, and basically structure one used for the list, and we have the pthread log. Here also we have the list, the pointer, head, pthread mutex, and we have the log. In the list insert, again this concurrent linked list, in the insert We have pthread mutex lock, and as you can see here, node T, we have new pointer. This is malloc, the size of node T. And so here, if you count, if it is 1, it is fail, and if it is 0, it is success. As usual, we unlock. And again here, list, concurrent list, linked list, where people have the same if this function returns 0, success, that pthread mutex unlock. If it is 1, it is failure. So the concurrent linked list, the code acquires a lock in the insert routine upon entry, and the code releases the lock exit. If malloc happens to fail, the code must also release the lock before failing. This kind of control flow has the solution is the law can release only surround the actual critical section in the insert. So the concurrent linked list, this rewrite, this is also as a code. I took it directly from the book, and pthread mutex initialization here, and synchronization not needed. We have just local critical section, as you see, lock and unlock, and it is sandwiched between lock and this pthread mutex lock and pthread mutex unlock. And again, as you can see here in the while loop, pthread mutex unlock, and now goes success and failure. That is the idea. So scaling linked list, handover, hand locking, lock coupling. This is add a lock the list instead of having single lock for the entire list. And when traversing the list, first grabs the next node lock and then release the current node lock. Enable a high degree of concurrency in the list operations. However, in practice, the overhead of acquiring and releasing lock for each node of a list traversal is prohibitive. And we have the other concept. This is Michael and Scott concurrent queues. There are two locks, one for the head of the queue and one for the tail. The goal of these two locks is to enable concurrency of queue, EQ, and DQ operations. Add a dummy node, then allocated in the queue initialization code, enable the separation of head and tail operations. So this is concurrent queue, the same node T and int value, turn next, head and tail. We have also mutex T for head and mutex T for tail. We have, this is for initialization, Q initialization, Q. We have also pointer Q and temp. Also the pointer for temp in one lock we will assign in the keep, and size of the T will be here. And next null and execute head and tail is equal to 10, and pthread mutex initialization for Q, head and tail like this. And Q EQs, this is for the EQ. What we are going to do, the node T, again we have temp. This is the pointer for the malloc function, and we have to give the site here, and we have to start. The assertion is here. And what other things? We have pthread mutex lock, and we have for the tail, and pthread mutex unlock, and this is the line of course. And for the DQ also the same. Pthread mutex lock, we have header here, then we have the pointer, and we have new head here. Okay, the pointer for new head, and pointer mutex unlock, and the Q was empty first here, and the return is 1. Then the value new head and new head, and we have the so concurrent table. This is another hash, and the hash table does not resize and built using concurrent lists. It uses a log per hash bucket, each of which is represented by a list. And this is also another product. You can see concurrent hash table. We have the definition here, bucket 101, the hash key, list, bucket, hash initialization, we have function here for I is equal to 0, I less than bucket, and we have to increment it. Then the list initialization is here. In the hash insert, so what it does is hash t, and we have the pointer h t. So int bucket, then we have the key and the bucket, and return the list insert, and the bucket and the key. Then in the hash loop, we have the pointer h and the bucket and the return list lookup, and we have the list bucket and the key. So this is also the full explanation of each line of code. What it does is explained in the book. I recommend you follow the book. So the performance of concurrent hash table, as you can see here, from 10,000 to 15,000 concurrent update from each of the 4 threads. Embark with embark with 4 Intel 2.7 GHz Core i5 CPUs used for wait the time, and we have the thousands. So the simple concurrent hash table in this case, as you can see here. So the concurrent hash table performs well here, but the simple concurrent list time goes when the simple table is a magnificent. Okay, so actually this was the idea of the part of 29. I hope you get something out of it, and I really recommend you to go through the book and read and practice the codes as well. And that was it. This was from here. And I meet in another video, and as you can see, this lecture slides, it was initially developed for operating systems course in the computer science at Anyang University and used for educational purposes at A1 Academy registers. This lecture slide set is for OSTP book written by and clear with inside. So thank you so much. I will